Alright, this is it. We've put this off as long as we possibly can. We have added vectors that are going the same direction. Not so bad, you just add the magnitudes. We've added vectors that are going in opposite directions. Not so bad, you just subtract the magnitudes. We even talked about then what happens if we don't have one of those nice cases, and we know we have to break the vectors up into their x and y components. But then even in our last example, when we had two vectors that were perpendicular to each other, we really didn't need to break anything up per se. They were already in their horizontal and vertical components, so all we had to do was use the Pythagorean theorem to find the magnitude and a little trig to find the angle. Finally, we've gotten to two totally random vectors that don't fit any of those other patterns. The technical term for that would be non-orthogonal vectors. We have vector A that's at a 40-degree angle above horizontal, and we have vector B that's at a 15-degree angle below horizontal. And both their magnitudes are also written down. And we are asked to add these two vectors, and so we need a total resultant, a total magnitude, and the angle of the resultant vector. So let's take a look at how we're going to do that. Alright, as we explained earlier, anytime you have vectors that aren't horizontal or vertical, you have to break them up into their horizontal and vertical components. So that's what we're going to do with each of these. It's a pain, but it has to be done with each of them. So looking at vector A, what I'm going to do is write down vector A itself, again trying to make sure I maintain its magnitude and direction, and then draw AX and AY. And I know that now in this triangle that I've made, there's a 40-degree angle over here. And so what I'm going to hopefully do then is solve for AX and AY. So here's what that's going to look like. AX is the adjacent side of the triangle. We obviously have the hypotenuse up here, that's our 4. This is the adjacent. AY, when we get to it, is our opposite. So to start out, to find AX, I'm going to use cosine, because cosine is adjacent over hypotenuse. So cosine of theta is AX over A. So A cosine theta equals AX. And so now we can just plug in some numbers there. You get 4 cosine 40. And when you dump that into your calculator, you should get 3.064 for the magnitude of AX. Alright, I'm going to do the same type of thing to find AY now, but AY is the opposite side of the triangle, so I'm going to use sine, because the sine of theta will equal AY over A. And so just rearranging algebraically, you get A sine theta is AY. And then just like before, we can plug in our numbers. So you get 4 sine 40, and that should equal 2.57. So there's the magnitude of AY, 2.57. So we just broke vector A up into its horizontal and vertical components. We have to do the exact same thing now with vector B. So you can see here I redrew vector B as well as I could, not changing its magnitude or direction. And then I drew BX and BY in to make ourselves a little triangle with the 15-degree angle. I'm going to once again start with X. BX is our adjacent side, so just like before, I'm going to use cosine. So cosine of theta is equal to BX over B. So B cosine theta equals BX. And so then just plug in a number, we'll get 6 cosine of 15. And when you do that math, you should get 5.79. Again, please make sure your calculator is in degrees mode when you're doing these or you get them all wrong. Last one then is BY. So BY is the opposite side of the triangle. So I'm going to use sine again. And what I'm going to do here is just take a little shortcut because you've seen me do this algebra 3 times. So I'm just going to move the BY over by multiplying both sides by B, but right in the same step. And I'm going to plug in my numbers, so I get 6 sine of 15. And when you plug that into your calculator, you should get 1.55. And so there's our magnitude of By, 1.55. All right, so all I've done now is I've erased our trig work just to make some space on the board here. So I got rid of all the sines and the cosines, but I did leave our original vectors, as you can see. And I also left the triangles, and I wrote in here the x and y components of each vector so that we have those. Here's the next step when we work with non-orthogonal vectors, as I called them before. Vectors that aren't nice and easy, aren't going the same direction, aren't going opposite directions, or aren't even perpendicular to each other. I said over and over again, well, if you don't have that, you have to break them up into your x and y components. Well, we just did that, so now what? Well, now what we really have here, if you think about it, is 4 vectors that we have to add up, not 2. So with these 4 vectors, what I see is I see an ax of 3.064. I see a bx of 5.79. And notice I just lined those up head to tail as I'm trying to add up my total. I see an AY of 2.57. And I see a BY of negative 1.55. The negative is important because we know that means it's going to have to go down. I'm going to just rewrite this a little bit. 1.55 going down. Don't forget this one was 2.57. And so really I'm just adding vectors, again, head to tail. So I have these two going head to tail. We now made this into a problem we know how to do. I know how to do vectors that are going the same direction. So if I add up these two numbers here, I should get a grand total in the x direction of 8.86. If I add up these two vectors going in opposite directions, again, a problem I now know how to do, I have 2.57 going up, 1.55 going down. I should get a grand total of about 1.02 going up. And so, once again now, I know how to do this problem. Think about what we did. Again, let's backtrack for 1 second. We had 2 non-orthogonal vectors. We broke them up into our x and y components. That gave us 3 more vector addition problems that we know how to do. Vectors going in the same direction, vectors going in opposite directions, and now I have 2 vectors that are perpendicular to each other. And so I know how to add those up just as well. Okay, so I just rewrote it down here to give us a little space and to rearrange my labels. So we know I need to find this magnitude and this angle, and we know how to do that. I just showed you how to do that with perpendicular vectors. So what I'm going to do here is I'm going to do the Pythagorean theorem, 8.86 squared plus 1.02 squared to get my resultant squared. And when you solve that, you should find that the magnitude of this hypotenuse, or the magnitude of this total resultant, is 8.92. And so that's the magnitude of the resultant. Don't forget though, we're not done until we find this little angle as well. And so we're going to need just a little bit of trig here to do that. I see that this y, this total y vector is my opposite side. This total x vector over here is my adjacent. And so just like before, I'm going to use tangent. So tangent of theta is 1.02 over 8.86. And then I just need to use that inverse tangent function. So theta is going to be inverse tangent of 1.02 over 8.86. And then we just dump that into your calculator. You should get a really small angle here. Specifically, if your calculator is in degrees mode, you should get 6.57 degrees. And so right there, circled nice and big, after all that work, you have the magnitude and direction of your resultant vector. So the sum of A and B, after all of this, is 8.92 units in magnitude and 6.57 degrees above horizontal.